So in this video we are going to use a bit of what we've learned already in the compound angle formulae and a little bit of kind of playing around with all of that kind of stuff to give ourselves a new technique for using trigonometric expressions like this one here. Now, as it stands, any of the crises I could come up against in terms of, the things that might bug us as mathematicians, so the ability to solve or sketch, to find highest and lowest points, things like that, I can't do. And the main reason I can't do that is because I've got both cos and sine in my expression. So I need a new technique, if you will, to get it into a single trigonometric expression, and then that way everything's nice and easy, and you'll see that in the next video. But what trigonometric expression, I hear you cry? Well, we do know that sine and cos are linked by tan, in the sense that if you divide one by the other, you do get to tan, but we've got no equals something, no other side to play around with. And this is something that people do all the time, and I just want to highlight it now. This is a no at the moment. No, 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 no. We're going to be a little bit more elegant than that, a little bit more clever. So I and you can be a little sneaky, and we can sketch this function using calculators, graphical calculators, autograph, that kind of stuff. And it looks a little bit like this, which looks surprisingly like a sine or a cos graph. So it must be possible to get this function into just cos of something or sine of something. The thing is, though, the one's down here somewhere, minus one's over here, and it's not positioned in any kind of normal way either. So we need to find out how much this stretch is worth, and also what the shift is worth from just a regular sine or a regular cos graph. So I'm going to pick cos. You could pick sine. As you know, they're already translations of each other, so it doesn't really matter. I'm going to pick cos because I think it looks closer to cos. Might be what the question tells you, so that's all right. I'm going to put my angle in. I'm also going to put plus alpha for a shift. So that's the alpha term that has shifted. If it's positive alpha, obviously it's moved it in the negative direction because it's on the x term. And then I'm going to represent this stretch, the amount beyond 1 that it's stretched, as r. So I'm claiming that these two things are in fact equivalent. It is possible to represent 5 cos theta minus 12 sine theta in terms of r cos theta plus alpha without losing any information, so maintaining exactly the same information there. Hence the three lines on the equals. Okay, so how do I actually do this? How am I going to go about getting it into that form? I think it's there. If I've sketched it on a graphing package, I know it's there, but I just need to know what those bits of information are. Now, you could hypothetically cheat and get the answer by looking at the maximum points on your graphing package, but that won't be enough for you in the exam. You'll need to show some method here. I'm just going to have a look at this new right-hand side that I've created, this r cos theta plus alpha. And I'm going to use the compound angle formulae to expand this out. So I'm going to say that that is r cos theta cos alpha minus r sine theta sine alpha. And these two things are still equivalent, so I can still write in that left-hand side. But now I have two terms separated by a minus sign, and so maybe I can start to equate some things. So if I have a look at what's happening around the cos thetas on both sides of this equation. So on the left-hand side, cos theta is multiplied to 5. And on the right-hand side, cos theta is multiplied to r cos alpha. Now, there is no other way for this equation to be identical to one another unless those two things are also equal. There's no other way I could generate any information. There's no information that could get collected into it. It is literally that 5 has to equal r cos alpha, whatever that is. Otherwise, this whole equation falls apart. Likewise, for the sine theta on both sides, I don't want to underline sine alpha, sine theta on both sides, minus 12 equals minus r, so I can just write that 12 equals r, and also sine alpha. So multiplied to the sine theta on the left-hand side is a 12, and multiplied to the sine theta on the right-hand side is an r sine alpha, and I've ignored the minus sign because it's there in both cases. So now I've got that 5 cos alpha, oh no I don't, I've got 5 equals r cos alpha, and I've got that 12 equals r sine alpha. Those are the two equations I've got. Now, it's good that I've got two equations because I've got two unknowns. I need to find r, I need to find what this stretch is, and I need to find alpha, I need to find the shift. Two equations, two unknowns. We're going to be doing some sort of simultaneous equations, but I think we could be a little bit more sneaky than that. And here's my sneaky step number one. I'm going to square everything. So square the whole of this side of the equation and square the whole of that side of the equation. And I'm going to do the same on the other little equation as well. And then I'm going to add the two equations. So say, okay, if I add these two equations, I'll add the left-hand sides. 5 squared, add 12 squared. And therefore, I must have added the right-hand sides as well. So r squared cos squared alpha plus r squared sine squared alpha. Keeps it still equivalent. We're still saying that if 5 squared is r squared cos squared alpha and 12 squared is r squared sine squared alpha, then 5 squared plus 12 squared must be the other two bits added together. It's not possible to be anything else. So 5 squared add 12 squared is r squared. Just factorise out that r squared. That leaves me with cos squared alpha add sine squared alpha. Now, I'm hoping everyone is going, ha ha ha, I know what that is. That is one of our trig identities. That is 1. So that leaves me with 5 squared plus 12 squared equaling r squared. And so r is just the square root of that. Well, that's 169 as it's squared. And so r must be 13. So in our original little function where we had our graph all translated, I now know that that highest point is 13, and that would make our lowest point minus 13 as well, because we've got that shift working in both directions there as our r shift. Stretch. Okay, so we found our r. We now know that r is 13. I've kind of got two options here, and it depends on what suits you. Now that you know r is 13, you can just substitute that back into the equations and solve those for alpha. But if you're enjoying this kind of mixing everything up, the technique that's most commonly used is that now we found r, we basically just, well, we don't even really need to worry about it actually, because I'm going to use the fact that sine alpha over cos alpha is tan. So I'm basically going to divide one of these equations by the other. So actually in both cases I've got r sine alpha and r cos alpha, and that one is 12 and that one is 5. So all I've done is stack them on top of each other. Now we know that when you divide and multiply by something, so in this case this r, it cancels. So I could have done this bit first, I didn't need to find r first. So I'm left with 12 over 5 equals sine alpha over cos alpha, and we know that sine alpha over cos alpha is tan. And so now I'm just solving this equation for alpha. And I believe that that gives me, should probably have a calculator handy, shouldn't I? 1.18 radians, presuming we're in radians here. So my shift, alpha, is 1.18. So if I think back to that function that I drew at the beginning, because we plotted it using a graphing package of some sort, this shift here is 1.18 and this stretch here is 13. So this highest point now obviously is 13 instead of 1, and where this maximum value on cos would have sat on the y-axis, it's now shifted, 1.18 in the negative x direction, because 5 cos, what was I doing? 5 cos theta minus 12 sine theta is equivalent to this structure that we thought of, r, which is 13 cos theta minus plus 1.18. Now, if you go and plot both of those equations, you'll find that they are exactly the same thing. You can't actually see two distinct lines. You've got one line there. And that means that they're equivalent versions of each other. You can write them that way. You'll learn in the next video that this is much nicer for solving things, for finding maximum and minimums, for using within the context of problems, because it only has that single trigonometric function. Let's run through one more example then, just to make sure we're all absolutely happy. So I'm going to write this one in the form r sine x minus alpha. Now, if you have to select your own, a couple of kind of general rules are really helpful. Picking cos and sine really doesn't matter because we already know that they're transformations of each other. So I suggest that you go for whichever trigonometric value comes first, because within the expansion of cos a plus b, cos comes first, and within the expansion of sine a plus b, sine comes first. So it makes it much easier for you to compare. Once that's decided, look then at the whether it's an addition or subtraction in between those two things. If it's a subtraction and you've picked sine, you still need that subtraction there. If it's a subtraction and you've picked cos, we saw in the other example you'd need an addition. So that will affect what you've got there. Ideally what you want is for the expansion term, so whether that's plus or minus, in the expansion to match this one. You don't want them to match now, but you want them to match when you expand everything out. And that is simply just to make your life easier. Much better to just think about it briefly when you start your question than to be worrying about pluses and minuses and some being minus and some being plus and which ones are which later on in the question. Saying that though, of course, if you are feeling confident, you can just go for it, just pick anything. It will all work out in the wash absolutely fine anyway. You just do need to watch the minus signs. So, I'm going to leave this on this side as we did before. That is not an alpha. That is an x. Minus 8 cos x. And I'm going to expand out this other side. So this is r sine x cos alpha from the compound angle formulae, minus r cos x sine alpha. If you're not sure about those, go back and watch the compound angle formulae video. Look back at your notes from class. It's really important that you get quite fluid with that. Okay, comparing the sine x's across this equation. Well, sine x appears on the left-hand side where I've underlined it in pink, and on the right-hand side where I underlined it in pink. It doesn't appear anywhere else. So we're just going to look at these two terms, and we're going to say, okay, for these two sides of this identity to be equivalent to each other, this 4, the thing wrapped around sine x, must equal r cos alpha. Looking at the cos x's in both sides of the equation, this 8 must equal the r sine alpha we've got going on the other side. Now, I don't need to worry about that minus sign because it's there in both cases. So I could have written that minus 8 equals minus r sine alpha, but then the minuses would have cancelled anyway. So it doesn't really matter. It's absolutely fine to just, because we've put all of that thought into the earlier stages, it's okay. We don't need to kind of go through those additional steps there. Okay, finding r then. Square everything. So 16 equals r squared cos squared alpha, and 8 squared, because I can't be bothered to work it out, is r squared sine squared alpha. So then 16, which is 4 squared, add 8 squared, must be r squared cos squared alpha plus r squared sine squared alpha. Factorising out that r squared gives me that. That is equal to whatever that's equal to. What is that equal to? 80? And cos squared alpha plus sine squared alpha is 1. So 80 must equal r squared, in which case r is equal to the square root of 80. I've had to move over on my page here, so I'm just going to scribble everything down again. So we found that r was the square root of 80, and as I said before, you can now just substitute that square root of 80 into the equation and solve one of them. You should check the other one though as well, just to make sure you're absolutely 100% right. As I've mentioned before, the most popular technique though, and the one that they're kind of expecting to see in the exam, is for you to divide one of these equations by the other to produce the function in terms of tan. So r sine alpha obviously is 8, and we're going to divide that by r cos alpha, which is 4. That leaves me with 2. The r's cancel, and sine alpha over cos alpha is tan alpha. Solving this then, we get that tan to the minus 1 of 2 is equal to alpha. Apologies if the video just went weird there. If it doesn't, I'm going crazy, but either way. So tan to the minus 1 of 2, chuck that in your calculator. That gives us alpha equals 1.11 radians. So we should have that, whatever our original function was, and I've absolutely lost the plot now, 4 sine x minus 8 cos x is equivalent to the square root of 80, which is 4 root 5 if you'd rather, sine x, Hannah, x minus 1.11 radians. Now, again, plot them again, check that they actually sit on top of each other. Stick a value of x into both sides of the equations to check, but checking, don't forget, is the name of the game. So find a way that works for you. Either expand out this side of the equation, check it does cancel back down to this side of the equation. I think I would stick with chucking an x value in. So pick a sensible x value. X is, I don't know, pi over 3, something you know that isn't going to freak out the equation too much, and just check that absolutely everything is fine, because for as long as your method is there, it will only have been a small slip up that will have caused a change in your numbers to any significant amount. What we're not trying to do here is prove that we're right. We've done that through the working. We're just checking. So we want to just find a very quick and easy technique to just validate to ourselves that we're right. So pick a nice value, x equals pi by 6 or pi by 3 or something like that. Chuck it in and just check that both sides of the equation still hold. Don't forget to check out the next video on actually using this technique. That one video was recorded to go as a sort of a prerequisite to this technique. So at the end it gets a little confusing, but persevere with it. It's absolutely great, and definitely worth watching.